So Newton's laws as they govern motion is the main focus of this unit. We're going to be exploring things like car crashes here. We're going to be looking at the dynamics of objects as they move. And we're going to be talking about the forces involved. Now, most of this stuff is pretty intuitive. You're probably going to find this a lot easier than what we've been doing. However, some of it does require some deeper thought, and there is going to be some math that we will be doing as well. Alright, so Newton's first law. He had three big laws. Newton's first law is an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. And that is kind of the key point there, an unbalanced force. Right? For example, right now, why am I not just spontaneously flying up into the air or falling down to the center of the earth? What's that? Well, the force of gravity is pulling me down effectively, right? And I'm exerting a force onto the ground, but that ground is exerting a force that is in equal and opposite direction. There is no net force, right? There's no unbalanced force. But if I were to apply an unbalanced force to, say, this book right here, I give it a little push, well, that object started to move. And as soon as I let go of the book, what happened? Started to slow down, and then it came to a stop. Another unbalanced force, the force of friction. Now, we are going to be learning about all of the different types of forces, but for now, this is the key point that you need to know. Right? If something is moving with a constant speed in a single direction, that object has no net force on it. It does not have any unbalanced force. An object that is completely motionless also does not have any unbalanced force. Right? Think of like the tightrope, not the tightrope, sorry, the tug of war example, right? You can have two groups pulling super hard on it, but if their forces are equal and opposite, that just rope, it won't move, right? It won't move at all. So a bit of a thought experiment for you right now. Suppose for a minute you had a pie plate and you filled it with water, and you decided you were going to go for a run around the track outside. What parts of your run would the water spill? What parts of the run would your water spill? Take a minute, just talk amongst yourselves. Think about it. What do you think? What do you think? Nick?
When you first start? Like that?
Sure, when you first start. Keep in mind, you are at rest and then you start to move forward. That water's at rest. Right? What's going to happen as soon as you start to move forward? What's that? You don't know? You're right, Nick. You're right, but what's going to happen to the water when you start to move forward? Which way is it going to spill? It's not going to spill forward. Remember, an object at rest stays at rest unless acted upon by an unbalanced force. So that water is at rest. It's going to want to stay at rest. And you're moving that pie plate out from under it, so which way is it going to spill? It's going to spill on you, right? It's going to spill on you. So if you accelerate really quickly, that water was at rest. You're taking the pie plate out from under it. It's going to spill on you. Where else is it going to spill? Yep.
When you slow down.
Sure, at the end of the race when you slow down. If I come to an immediate stop, what's going to happen to all that water? Yeah, it's going to spill out and go forward. And there's one more time it will spill as you go around the track. Yeah?
When you change direction.
Yeah, when you go around the corners, right? An object in motion wants to stay in motion. So when you go around that corner, which way is the water going to spill? Yeah, it kind of went to the side, right? If you're traveling straight, that water, you've accelerated that water up, right? And as soon as you start to turn, that water wants to continue in its direction of motion, right? An object in motion will stay in motion. So it will spill as you round the corner as well. Does that kind of make sense? Okay. Understanding that is really essential to understanding other things, like why is it that we need to use seat belts in cars, for example? Well, what happened to the water when it came to an immediate stop? What's that? Which way did it spill? It came to an immediate stop, what happened? Water flew out that way. Now, if you're in a car, and let's say you're driving, I don't know, 100 kilometers an hour, and then you hit something and you come to an immediate stop, what's your body going to do? Yeah, you can go flying. You're going to Superman through the windshield, right? An object in motion will stay in motion unless acted upon by an unbalanced force. And you need that seat belt to be that unbalanced force. Otherwise, you're going to keep moving in the same direction with the same speed, and you are going to fly through that windshield, which is way more dangerous. So, understanding this is pretty important. Alright, so the water spills whenever its state of motion is changed. Sorry, whenever the state of the motion of the container is changed. The water tended to keep doing what it was doing. Right? An object in motion will stay in motion, an object at rest will stay at rest. You have this all in your notes, correct? Yeah, okay. What do you think I mean here by state of motion? Well, let me ask you something. Do you think the water would have spilled if I was traveling just at a constant speed the entire time? No, why not? It only spilled when I changed what? You guys are good. My acceleration, right? So when I say state of motion here, really I'm referring to acceleration. So, inertia. This is another big concept, one that you will be practicing today in your workbooks. Inertia is the tendency of an object to resist changes in its state of motion. And you guys already figured that out. What is meant by state of motion? Well, your state of motion is defined by its velocity. Now, we can redefine inertia here, my remote's dying, as the tendency of an object to resist changes in its velocity. So it's the tendency of an object to resist changes in its velocity. What do we call a change in velocity? You guys already said it. Yeah, it's acceleration, right? So we can reword this to be the tendency of an object to resist acceleration, right? The tendency of an object to resist acceleration. Because any change in velocity is an acceleration. So let's say, for example, I'm going to pick on you, Logan, here. Let's say, Logan is lining up on the football field against a professional linebacker that weighs like 400 pounds. Who do you think is going to knock each other over? Do you think Logan's going to knock the 400-pound linebacker over, or the other way around?
The other way around.
Yeah, probably the other way around. You never know. You never know. Logan's a pretty good athlete. But why is that? In fact, if you tried to push the 400-pound linebacker, he would probably barely move, where if he gave you a good shove, you would probably move quite a bit. Let's use a different thought experiment. Let's say that here I am applying an unbalanced force to this book here. What if I tried to apply that same unbalanced force to, say, like a train? Do you think I'd be able to move the train? No. No. Why not? Yeah?
I don't know, but it has, since it's heavier,
Ooh, that's a good word, yeah.
more weight when it's down.
Sorry?
So it's like, I don't know, it has a stronger base.
Yeah, I see what you're saying. It has to do with mass. You are right. So when we look at inertia, inertia has a lot to do with mass. Now, before we break down how mass affects inertia, let's quickly look at this example here. Now, a 4-kilogram object is moving across a frictionless surface at 2 meters a second. Which one of the following horizontal forces is necessary to maintain this state of motion? What do you think? What do you think? I'm going to start to pick on random people. Alexandra, what do you think? A? Who here agrees with Alexandra? Is it A? Who here thinks it's B? Show of hands. C? D? Okay, we have an E. The answer is A. You guys just left her out to dry. Only one other person raised their hand. The answer is A. Why A? This is a bit of a trick question. Why did you think it was A?
Because like inertia depends on mass rather than speed.
Sure. You're right, but that's not why it's A in this question. Newton's first law, an object in motion will stay in motion unless acted upon by an unbalanced force. Now, this object is traveling at 2 meters per second on a frictionless surface. Therefore, there is no friction to slow it down. It will continue with that same speed in that same direction forever. Without a force acting upon it, it will continue at that constant speed, right? Just like if you were out in outer space and you push something out into the dark, right, it would continue with that same velocity in that same direction forever until it interacts with a planetary body of some kind, right? So, 0 newtons. So if you have something traveling at a constant velocity, there is no net force acting upon it. Here we go. Now, do some objects have more of a tendency to resist changes in their motion than others? Well, the answer is yes, right? The answer is yes, and it has to do with their mass. So the more mass of an object, the greater the tendency to resist changes in its state of motion. And we already talked about state of motion. How did I redefine it? You're resisting what? I thought I heard it whispered there. You're resisting... Well, state of motion is going to be resisting changes in your velocity, therefore you are resisting acceleration, right? So the more mass of your object, the greater the resistance to acceleration, right? That's why when you are stopping a train, for example, when a train's coming into Winnipeg, it's traveling pretty quickly. If it needs to slow down, how long do you think that takes? When do they start slowing down? A really, really long ways away. It takes a lot of force to slow that train down because it has such a great resistance to acceleration, right? To slow it down, to decelerate the train, it has a huge resistance to acceleration, so it's going to take a really long time. Which is why if you have a car sitting on the train tracks and a train's coming, lots of the times the train's not going to be able to stop in time, right? On the other hand, if you have an object that's very light, it doesn't take much force to slow it down. Here's a bit of a thought experiment again. Suppose you had 2 bricks on your table. One was made of mortar, so it was heavy, right? The other one is made out of styrofoam. Now, both of these bricks, you have like a talented artist that comes along and paints them all up. You cannot tell them apart at all. Okay, there's no way to tell them apart. They feel the same, they look identical. Now, without lifting these bricks, how could you tell which one is styrofoam? How could you tell which one is styrofoam? Excellent. Push them. If you push them, what's going to happen? You give both of them an equal push. Right?
One is gonna move a lot farther than the other.
Yeah, which one's going to move further? The styrofoam one, right? Because the mortar brick has a greater inertia. It resists changes to its motion. It resists acceleration. Right? So if you give both of them an equal push, the styrofoam brick will go further than the mortar brick. Right? Think of the example. If I gave Logan a shove or like a 400-pound linebacker, the linebacker's probably not going to move very much. It has a lot more mass. So the styrofoam brick will go further if you give them an opposite push. Equal push, sorry. Now, this would apply pretty much everywhere. This confuses students because there is a question in your worksheets that involves pushing things in outer space. And students often think outer space is like something special. The laws of physics here on Earth are the same laws of physics in outer space, just FYI. As far as we know, we think all of the laws of the physics are constant across the universe. Here are some other examples of Newton's first law. Has anyone here heard of the Burj Khalifa? What is the Burj Khalifa? Nick?
Isn't it like the tallest building in the world?
Yeah. It's the tallest building in the world. Now, originally when it opened, they had people like fainting on the elevator. Or starting to faint, right? They were getting lightheaded. Why do you think that is? Sorry? Not oxygen deprived, no. No, not oxygen deprived. By the way, it's pretty cool. You can actually watch the sunset at ground level and then take the elevator up to like the top and watch the sunset again, which is kind of neat. But originally, you would get super lightheaded if you took their elevator. Give you a hint, they actually had to slow their elevator down. Slow the rate at which it accelerated and decelerated. Think about it. If you are at ground floor and this elevator starts to accelerate rapidly, well, what's going to happen to the blood in your body?
Go down your legs.
It's going to go down to your feet, right? An object at rest will stay at rest. So your blood will go to your feet. And as a result, you're going to get lightheaded and you can possibly faint. Right? Same thing when the elevator stops. Actually more common when the elevator stops. If you are moving down and the elevator is slowing down very rapidly, that blood's going to go to your feet because your blood is moving, and an object in motion will stay in motion. As you decelerate, that blood's going to go to your feet. Now, a more extreme example of this would be jet fighter pilots. Do you know what they wear? It's like the most uncomfortable suit of all time. No one dreamed of being a jet fighter pilot when they were a kid? Well, what would happen? I'm in a jet fighter plane, right? And I bank and I take a corner really hard, right? So I bank the plane and then I do a crazy turn. What's going to happen to all the blood in my body?
It's going to go down your feet.
Yeah, it's going to go to your feet. You're going to pass out, which would be really bad if you're flying really fast. So they actually wear special suits that are pressurized, that they will actually like clamp down on your legs and try to keep blood in your head. So it clamps down on your legs, clamps down on many parts of your body, and restricts blood flow so that it keeps it in your head when you're doing crazy high-speed maneuvers. Wildly uncomfortable. Another good one, hammer. Anyone here has ever had to put a head back on a hammer? The way you do it is not by trying to smash the head back onto the shaft. That is not the way you do it. If you have your head fly off of your sledgehammer, the way you're supposed to put it back on is you place the head of your hammer onto the shaft, and then you smash it down on the table. Now clearly this didn't work with my marker. Why is that? Yeah, exactly. My head of my marker here has no inertia. Well, it doesn't have no inertia, it has low inertia, right? Because it's very, very light. But your head of your hammer is extremely heavy, right? It resists changes to its motion. So it's going to keep going and it's going to ram itself onto the shaft, your hammer shaft. So that's how you put a hammer head back onto the shaft. Another big one here, headrests. Headrest is another big one. So anybody here know why they have headrests in their cars? Before taking grade 10 science, everyone has the same answer. It's because they're comfortable, right? It's because they're nice and comfortable, you can lean back. But why are they really there? Think about it for a second. You're sitting at a stoplight and somebody creams you from behind. What's going to happen? Let's say you're cruising like a really, really old boat of a car, one that has no headrests, right? And the seats go up to about, here-ish on your back. What's going to happen? When you hit from behind, is your car going to move forward? Yeah. What isn't going to move forward with your car?
Your head.
Excellent, Nick. Your head, right? Your head. So people think that their head snaps back when they get hit from behind, but that's not the case. What's happening is your body's actually moving out from under your head. So it's moving out from under your head, and that's why you get that whiplash. So headrests are actually meant to keep your body accelerating, all of your body, your head included, accelerating so you don't get whiplash. Right? Otherwise, your body's going to accelerate out from under your head, and you are going to have your head whip back, and that is going to cause whiplash. So headrests are another important one. So key takeaways from today. What is Newton's first law?
At rest, stays at rest, and object in motion stays in motion with the same speed and does same direction unless acted upon by unbalanced force.
Yes, excellent. Now the key thing, unbalanced force. So if I have an object that's traveling at a constant speed, is there an unbalanced force on that object? If it's traveling at a constant speed in the same direction? No, there isn't, right? I know it's kind of hard to think about, hard to visualize, but no, there is not. Second big takeaway. What is inertia? It's resistance to acceleration, right? So the more massive an object, the more it will resist changes to acceleration. AKA, it's really hard to get a train moving. It's really easy to push a book across the table. Okay. Let me know if you have questions.